Thank you very much. It's a great pleasure to be here, and thanks in particular to Bảo Châu for the opportunity to give this talk. Okay, so I'll be talking about representation theory and harmonic analysis on P groups, and so F will be a local non-Archimedean field. And so later it will be an equal characteristic for safety, and we look at representations of a reductive group, so the G say this split reductive. Classical objects of study is the theory of smooth representations and characters, and of course the local Langlands conjectures predicts classification, and then the theory of L packets of irreducible representations, and then endoscopic properties including stability of combinations of characters, including stability, and so what I want to do today is give a kind of first an attempt to restate or complement these conjectures in the following way. Let's we take the full Hickey algebra, locally constant, compactly supported measures, but just for brevity I like this way, as identified with functions by choice of our measure. And then we have the cocenter Hg, which is of course H modulo the commutant, is C, the cocenter. And just by definition, an invariant distribution is an element, is the same as an element in the dual space, just linear dual. This is the space that contains characters. So character of an admissible representation. And so the plan, first I will state a general conjecture describing C in terms of Langlands parameters. And then results in the kind of special, but so and so results in this direction in some special cases, non-special cases. And so this is, maybe I should mention right away. So it's based on a joint paper work with Yakov Warszawski and work in progress with Dan. And also Yakov and David Kazdan and also Yakov. Sure, this is not public yet, but so these are all examples in depth 0, but this is unipotent case, and this is generic depth 0 characters. And if nothing else, this sort of conjectures summarize our thinking about these examples. Okay, so let's recall the setup. So, of course, we have this Galois group of bar over F. Goes to, so everybody knows. And so let's have inertia group. So this is, sorry, I may be using unorthodox notations, and so this contains the way group. To Z. And we so recall that the linear Langlands parameter is a pair so yeah, maybe just to simplify notations, I fix a splitting, fix a Frobenius, so the image is generated by Frobenius. So for representation rho from gamma to G check, where so rho of gamma 0 is finite, and rho of Frobenius is semi-simple. So you can say every image of any element is semi-simple. In any case, so and then rho, and then there is a element U, which commutes with gamma naught. So this is a unipotent in G check, which is unipotent. And then commutes with rho of gamma naught, but rho of Frobenius you dilates it by Q, where Q is, of course, the cardinality of the residue field. Okay, so this is just copying the classical definition. So now I want, I will be only considering what I call the inertia Langlands parameter, where I just this rho will be only defined on gamma 0. So let L be the stack parameterizing the data as above, except that rho is only defined on gamma 0. So this is like inertial Langlands parameter. So U is just commuting element. And now this L, and then Frobenius acts on this so by conjugation. And so this is a disjoint union, so since you cannot deform a finite image homomorphism, so this is a huge disjoint union of all possible homomorphism from gamma naught. So Frobenius acts on L by conjugation. And now, finally, something a little bit interesting happens. So I consider Z the inertia stack. So inertia is used in a different sense here. Of course, when I say data is above, I mean it's modular the conjugations by G check. So inertia stack of L. So what does this mean? So this is just Z parameterizes, to be very explicit, homomorphisms from gamma naught to G check. U commuting with, and then there is additional element gamma, so that everything commutes. And so U is unipotent, gamma is any, and yeah, rho of G U gamma or pairwise commute. Right, so this is a kind of inertia stack. It's a points in inertia stack. It's a point in your stack plus an automorphism. So this is the point in my stack, and this is the automorphism. So we should think of this gamma as endoscopic parameter, and the way it's, again, maybe I should say it before, so of course this is all motivated by shift theoretic approach to things. And this, conceptually, the origin of this inertia stack is because exactly we have categorical cocenter for the category of coherent sheaves on a stack. It recovers this inertia stack. But this is somehow we think about it. And Frobenius still acts on Z.
When you say the stack parameterizing this data, I suppose you want to relax the semi-simplicity of Frobenius?
There's no Frobenius, so that's.
Okay.
So rho is from gamma 0. Yeah, that's a good point. Thank you. Okay? Yeah, that's kind of one of the key points. So idea, and yes, Frobenius still acts on Z by conjugation. And so idea that is recover this C from the category of coherent sheaves on Z with an action of Frobenius. And so, so a little digression how we recover it. And so small digression, kind of decategorification. So when we have our category with a function, we want to recover a vector space from it. And maybe the prototypical example that we should be thinking of is we have a category of L-adic sheaves on a scheme, and we want Frobenius, and we have Frobenius, and we want to recover the space of functions and on FQ points. So there were different things in the literature, and maybe one notable example is the work of Kazdan and Lamont from the 80s. And then now in people, this appears a lot in the literature, and people consider this trace of the functor, which is essentially self-x or self-tors of the identity functor, so which a priori gives you a complex. And so we consider a different and more elementary construction, which actually produces the more relevant result for us. I'm not saying it gives the same result as this trace of identity. I'm saying that this is what we want. And so I have some abstract situation. So phi and like maybe endo functor of phi. Some abstract, well, triangulated, and I will skip over the standard issue of non-functoriality of cone. There is not relevant for us. You can think about a billion category. And then we say we take the K group, K phi Q, and we fix Q in our field of coefficients, which may well be C, but non-zero. So we take the following of C. It's by definition, I have the Grothendieck group of the category of equivariant objects, which is very huge. So this is the category. So this is where I'm being sloppy about. I mean, so usual issues with triangular categories, but this is easy to deal with. Equivariant objects. And then I do the following, and I tensor. So this is very big. So this is a category of vector spaces. You get kind of huge answer. But you can just kind of kill this irrelevant part by tensoring with K of, if you like, Z modules. Meaning finite dimensional C over C with C. So what is this? So this is just, again, it's a K group of, it is basically this example when have vector spaces. Anyway, so this is the category, this is the category of finite dimensional vector spaces with an invertible automorphism. And by Jordan normal form, this is nothing but the group ring of the multiplicative group of. Yeah, I assume that this is, sorry, I mean, it's the same field, so C is also C linear. And then this maps to C by sending lambda to lambda. And so this is my construction. I'm not saying it does a job recovering.
Lambda is Q? Oh, no, I mean, what is Q?
There's no Q. It's C.
You fix some.
Right, sorry. So there's Q is just a symbol, and it's not a very good symbol. So maybe let me adjust notation. This canonical construction. Right, sorry. The reason for this notation will be. Sorry, I dragged it from some other place in there. Okay, thank you. There is no Q. It's canonical construction. Yeah. So what? So quick examples. Yeah.
Just a question. So if instead of the inertia stack, we look at the intersection of the diagonal with the graph of Frobenius, and I mean,
this is Yes, this is related but different. So it's just kind of, I'm saying that, you know, it's maybe somewhat related to what other people do, but like Xinwen and well, Scholze in a more sophisticated setup, but we kind of walk this diagram in different order. We work geometrically and introduce Frobenius later, and they kind of. But you can do it, but it's kind of.
But it would be a different category than C fixed by phi, I suppose. I mean,
It's a yeah. No, it's a different category, but yeah, there are some diagrams you can write, but maybe we can do it later. Thank you. Yeah. So maybe example is we have C's coherent sheaves. Suppose we have some X with an action of GM, like algebraical, right? Yeah. And then we have Koch GM of X. And then if you just take the K group of Koch GM of X. Yeah, so here, this was a mistake, sorry. So we take a then this is a module over Z of, you know, TT inverse, obviously, because you just can just twist by character of GM. But now you can fix Q. Say we walk over C. Then we can fix Q in C star. And then, then we get an automorphism of X. And then we have K phi. Well, phi is Q kind of now. And then K phi of C. At least it clearly admits a map from K of Koch GM of X tensor over Z of TT inverse with C where T goes to Q. So I mostly often work with this example, so that's why I put the notation, but yeah. In some examples, I don't know, like I need to think about non-optimal conditions, but you know, sometimes in isomorphism, can check it's an isomorphism in examples relevant to us, but maybe it should be true more generally. And another thing is that just reformulating, I would say obvious corollary of say, Lustig's theory of character sheaves is that if I take C is character sheaves on the group over Q bar, and phi is Frobenius, then K phi of C is so it recovers functions on FQ points in this situation like that, where you have kind of a category where you know that certain irreducible objects generate the category. I'm not saying that in more geometrically interesting settings. I mean, you obviously have a map in one direction, but I'm not saying it's going to be necessarily an isomorphism in other more interesting situations. Okay, so, okay, and now I can just say that, so conjecture is that K. Yeah, we have phi equal to Frobenius of Koch Z is isomorphic to the cosine. Canonically. And okay, so now there is a further plus, I mean, this when characters of, say, temporal representations would be linear functionals on this. And so we can, in these terms of tempered characters and endoscopic pieces, but I will let me not spend time now on this, so I will want to pass to examples, and maybe I will say what we know in examples. Okay, so in all our examples, so of course, gamma naught maps to ZP, so this is like tame inertia, like monodromy. And so I will only look at tame parameters which factor through this. And so a tame parameter meaning it's factoring through Z hat P, it's the same as like an finite order, an element S in G check of order prime to P. So we'll only consider those. And so now we consider example 1. So we assume that S is regular. Yeah, I should say right away that the Z is a union of many, many pieces. But of course, only the pieces for which Frobenius of rho is conjugate to rho contribute. And so this is maybe direct sum over all rho from, again, from gamma naught to G hat, such that rho Frobenius is equivalent to rho. So in this case, this just means that S to the power Q is equivalent to S, conjugate to S. And let's say it's very regular, so the centralized is a torus. So this just means that the S is in Q check. And so S to the Q is W of S for some W in the Weyl group. And here too, we assume that W is elliptic, which means that it doesn't have the one eigenvalue on the torus is 0, and so on T check. And so T check W is finite. So this is some finite abelian group. So things really become rather simple. Yeah, let's just fix. So I want A to be the dual, Pentragian dual group this is A star. Okay, so let's just see what this definition tells us. So U is anyway 0, so we can forget about it because there's no centralized as a torus. And so all there is the action of so the component in Z is nothing but T check mod T check. And on which Frobenius X by W. Okay. And in this case, so we need to consider this KW of T check mod T check, and I'll give you an answer. So, well, this is like an exercise. That this is isomorphic to functions on the fixed points. By the map sending, so this is essentially equivariant Sheaves, so it's essentially Sheaves equivariant for like T check smash like W on T check, and then if you have such a, so this is my C, like equivariant objects as this. And then if I have some object here, then I send its class to a function which, you know, on a fixed point T, you go to trace of W on that point on fx as usual. And you can ask what is this? Why am I not using the other kind of elements here? But I don't have to use them because they anyway conjugate, in this group they anyway conjugate to W because W is elliptic, so it's okay. Okay, so now this is this kind of reformulating so a kind of a reformulation of a theorem with Yakov. So we basically to this, you know, people know what Langland's correspondence should assign to such things, and so this is the L packets, so consisting of induction from a paraphoric of the linguistic representation corresponding to. So maybe before our theorem, we'll just say that. So it's known that these parameters correspond to L packet of the form, so you induce from K to G of the linguistic representation. So it's cuspidal the linguistic representation. So which one? So to this element S, you assign a local system, and then there is the linguistic representation. So maybe one thing I want to mention here is that, well, there are several terms in the L packet correspond to several choices of this maximal compact. And now, well, maybe X. And in fact, X naturally lies in A, in this group A that I mentioned. So you can think of it as a fixed point. So you have an apartment for G and W X there, and you take the fixed points on the apartment. So it's and since apartment is kind of dual, then you have this duality. Fixed points of W on apartment of G mod integral translations. And so our theorem essentially says that there is a natural map of so KW of T check maps to so here, because all representations are cuspidal, kind of there's no big difference between the corresponding part in the center and the coscenter. So it maps to invariant distributions, and so that the corresponding points, so the delta function of some point y in T check W goes to kind of character sheaf on loop group, function coming from the character sheaf on loop group. And the elements in A corresponding to the characters of this group, they go to irreducible characters. Elements in A which is characters of T check W go to these irreducible characters in the L packet. And just a couple of more words about that work is so remark. So first we deduce the endoscopic properties. Meaning that the function corresponding to the character sheaf is endoscopic as it should be. And of character sheaves, so this follows deduced from a theorem of Yoon on compatibility of centralizer action and Springer action. Actions on cohomology of affine flag variety, of cohomology of affine Springer fiber, and given. So this gives this works for functional fields, but similar result without like character shift technique. So the similar result on the L packets. I mean, in the mixed characteristic case, were obtained some time ago by other methods, by trace formula methods, by Kazdan-Varshavsky and independently the Baker-Reader. But somehow the point of our work is that, well, technically maybe the case of equal characteristic was new, but the real point is that there is this geometric way of thinking about it. Okay, so now I still have a little bit of time, and so I can pass to the actually interesting example. So when rho is trivial, so S is 1, so rho, so it's gamma norm 0 to 1. Then the corresponding piece in Z so this is this commuting stack. So it's in subvariety in G. Well, I'll identify just for no reason. I will take a log, identify unipotent unipotent elements with nilpotent elements, and so this is the set of pairs X gamma, maybe E gamma, such that E is nilpotent and gamma E is equal to E gamma. And here Frobenius acts. We have action of Frobenius, which sends E gamma to Q E gamma. And so this is must and does correspond to the unipotent part of the center. So I recall that we have splitting, I mean, if you like, first Bernstein center has a splitting, and then it induces splitting of like H as H unipotent plus H non-unipotent. So for GLN, this is just unipotent representations are those which are generated by Bahori invariant vectors, but in general there are more. And so C unipotent plus C non-unipotent. In the theorem of our project with them and David and Yakov is that so here is now that the C unipotent is isomorphic to, well, K. Well, so here, for obvious reason, now I want to call this Q. So that's so CQ, KQ of Z. But now, before maybe in the remaining time, I want to sort of give different forms of the Sanse and various complementary kind of results and conjectures. So it's good to connect it to other things people know. Okay, so first of all, like maybe one of the, so let's kind of try to analyze it. So now I want to do like an exercise, or maybe a couple of exercises on the coherent side, pure in algebraic group theory. So one thing to sort of notice is, of course, that this thing is filtered by nilpotent orbits. But in this case, so it is a standard idea that this gives a filtration on the K group by orbits. So in this case, since Q is not root of unity, we can deduce that this filtration actually gives a direct sum decomposition. So I just continue this theorem. So this is equivalent to direct sum, isomorphic direct sum over all nilpotents. So n is the nil cone of G-check, modular conjugation of something which is some very classical object. So just now just the Grothendieck group of equivariant coherent sheaves. So ZE is the reductive part. I mean, it probably will be the same if I just take the centralizer of E G-check, and I take the Levy subgroup, maximal reductive subgroup. Yes. So now I come to this next exercise, that what is this? I mean, okay, so this is really what sits over the orbit, right? So over the orbit, I just have a point, and then by Frobenius induction, I really need to look at the stabilizer and action on it. And then the radical doesn't matter when we do the K group. So again, the fact that it's filtered with these graded pieces should be really clear, but it actually gives a splitting. Yes, so now how to compute. I mean, apparently it's not in the literature, although it could have been. How to have reductive group and how to compute this. And well, one answer, if the group happens to be connected and simply connected, then the answer is boring. It's just the same as equivariant sheaves on the point, just a representation, a ring of the group. But of course, this may not be connected and may not be simply connected. So we can do the proposition is that if H reductive, then KH of H is isomorphic to what I'll write the notation, so OL of so what does this mean? So this is the set of regular functions. So first of all, COMH is just a set of commuting pairs. It's a set of all x, y in H times H such that x, y is equal to yx. And now I consider invariant regular functions. Yeah, invariant under conjugations, with one additional condition that for any y, f of like maybe if I write f y of x is f of x y, then this new function will be locally constant in x. Is locally constant. So I can easily write an arrow this way for you, and maybe I will. In fact, arrow can be written more generally, but I don't know under what general conditions it's an isomorphism. But the arrow is I take f and I send the class of f to a function f. Well, I mean, it's in, I think that's probably the formula that came to your mind. So it's a trace of y on fx. Of course, you have to take derived fiber, but that's okay. But the point is that it's not locally constant y because, I mean, it's just some representation of the group and some class functions. But if you vary x by basically a local constant of order characteristic, this trace cannot, like some representation of algebraic group varying in family, it cannot change, it cannot jump. Okay, so that's okay. So now we are ready to state some statements which unfortunately have not been completely proven, but hopefully we're getting there slowly. But okay, so maybe I want to add a kind of a complement to this. So now we combining these equalities, we write that C important is the direct sum over E of this, or L. Again, L is for left, so it's just because it's locally constant in the first left variable, not the. Okay, just a quick remark that like an interesting feature of this, even the sort of, if you forget the details, just the feature that is tested here is that the center is splits as a direct sum over these Langlands parameters over E, and this is not really obvious from the definitions because, but so C unipotent, it contains as a direct summand the cocenter of the Hecke algebra. And the splitting for this can be obtained in a different way. Follows from other results from my a result involving asymptotic, elastic asymptotic Hecke algebra. Okay, it's not the focus of my talk, so I don't want to spend too much time on it. But I think it's kind of nice and perhaps has potential for generalization. So, so for lack of time, I will not recall the definition. I'll just say very briefly that, this, H is, I use notation. So here H affine, so this is H affine is the affine Hecke algebra. Okay. And it can be, although it can be defined from the Spedia group, but it's well known that it's really some family of algebras where Q is a parameter. J was defined by Lustig as sort of by Q kind of tends to 0 in the definition of the affine Hecke algebra, but I will not. The precise definition involves Kazhdan-Lustig basis, although Kazhdan-Braverman had some different description which generalizes. In any case, so what I want to say is that so J is actually, as an algebra, it's a sum over E of this JE. And the theorem that we proved with some guys with my former student Dobrovolska and Braverman's student Davidiak. That so H, Lustig constructed a homomorphism from H to J, but he called it phi. But so Lustig, our result is that H is that this homomorphism induces an isomorphism on cosenters. So we get the splitting. And by the way, while I am at it, I want to say that this J is also related to geometry. So there is this theorem with my students Karpov and Krylov saying that JE is Z equivariant coherent sheaf, is a K-theory of Z equivariant coherent sheaves on the square of the Springer fiber. So this was conjectured by Chiu and Shi, I guess. Okay, so, but this was a digression, so still maybe have 5 minutes, and so I return to my main story. So, yeah, so now we have this description for the center, and I also want to write this so inside the center. So definition. So there is a compact part of the center which is defined as follows. C is the space of, as we said, it's functions, compactly supported functions on the group, and you take coinvariants. So if I have any conjugation invariant set, I get a subspace. And so let's, so this is just, you take the functions on compact elements, union of compact subgroups, and then you take G. And then I take C kind of, C unipotent to be just the intersection. And so the last part of this theorem is that if you again rewrite the C unipotent as a direct sum for L of GE, again this is L and this is E, then this contains C unipotent, and this, so this is the new part, that this is the sum of OR, and now I have like L, and then I write R. So of G. So this means that before I only wanted it to be locally constant in the first variable, now I want it to be locally constant in the second variable. And now with this I can finally give the kind of complete this picture with the statements which are unfortunately still conjectures, but there are approaches. So we need to so first recall that parameters given E like S and psi, we use parameters where S, E, and N, S as a in G check semi-simple, and it commutes with, yeah, I want it now to be like that. And psi is an irreducible representation of the pi naught of the centralizer. to this we can assign a standard representation. And okay, so I assume G is simply connected, and so I assume G is adjoint, and so G check is simply connected, and so otherwise I would have to talk about inner forms. So assume and now on the other hand, so let's call it R as u psi, and then the functional. So now with this, from this data you can write an obvious linear functional on my space. And so the character of R as u psi corresponds to linear functional. So maybe I'll finish in maybe 2 minutes. Linear functional on C, again, which is direct sum of the E of OL of ZE. And so if I say here, if I take here some element F, which is collection of functions FE, then this would go, so F would go to the pairing of FE restricted to Y being equal to S, and then you pair it with the character of Psi. I mean, there is the only thing you can write. But then you can then the last thing you want to do is maybe I'll say it without writing. So you can restrict this to the compact part, but the compact part, because of this symmetry between left and right, it admits this flip of the two parameters. You can flip the endoscopic parameter in Frobenius, and if you flip, then you are getting, I mean, the conjecture that you get functional corresponding to like a character sheaf on the loop group and belonging to the corresponding endoscopic components. And the remark here is that kind of things match because these character sheaves on loop group, they by definition they obtained from some Springer sheaf tensoring over the affine Weil group, and by definition they all sit on compact elements, so you just don't touch. So this kind of makes sense here. Okay, so maybe I'll stop now. Thank you.